All right. We have this beautiful little. All right. So this is another problem, and it's asking what the limit as x goes to 0 is for this equation. So we see, well, as it goes to 0, this is going to be 0, and this is going to be 0. So we have a 0 over 0 equation, which means we got to start factoring. And our goal whenever we're factoring is to cancel out the denominator, because that's really the problem with it. But, you know, x is just chilling. It's not much we can do with that. So what we actually need to do is start messing with the numerator to get it to cancel out this x. So, and our numerator has rationals, like that's really hard to deal with. And it'd be really good if this rational wasn't really here. But how can we do that? Well, we know in our previous example that, you know, any a squared minus b squared, ooh, that looks really weird, was just a plus b times a minus b. And right here, we have an a minus a b. So why don't we just multiply it by a plus b to get our a squared and b squared? So we get rid of these rationals. So let's do that. So we're going to multiply it by a plus b. And this is called the conjugate, in case you wanted to look that up. Boop, boop, boop. And then we have to do it by the denominator too, so that we, you know, keep the ratio of the expression stable. And so, you know, we do our little foils. So the first is just, why does it do that? Oh my god. Sweet. It's just x plus 2 squared. The inner is negative root 2, root x plus 2. The outer is plus root 2, root x plus 2. And the last is negative root 2 squared. Sorry, I don't think you can see that. But, alright. Oh my god, why are you doing this? No. Okay, sorry. So, these two cancel because we have a negative this and a positive that. And the square root of a rational is just the inside of the house, and the same thing for this, but it's negative. So we'll have x plus 2 minus 2 over this multiplied 2. So it's x root x plus 2 plus root 2. And those two cancel, so you have x over x root x plus 2 plus root 2. And those cancel. So you've finally canceled your x. So you have 1 over root x plus 2 plus root 2. And again, this, we were computing the limit as this goes to 0. So if we've factored this out, it's the same thing as the limit as x goes to 0 here. And this is because, you know, our little note here. Let me just close that, try and look for it. This, that if f of x equals g of x when x is not a, then the limits are the same. And that's the same property that we're using right now, because the only reason why we were able to cancel out this x is because we're thinking about this x when x is not 0. So when x is just super, super close to 0, you know? So we're canceling it. I don't know. You can just ignore that. It doesn't make sense. We just canceled it just because we wanted to. So anyway, we're still computing the limit as x goes to 0, and that's really easy for us to do. It's just 1 root 2 plus root 2, which is equal to 1 over 2 root 2. And that is our answer. And we are good. Alright. So this next problem is just like a little sneak preview of what you're going to do later in the year, but I still wanted to put it in. So say you have this, and it's asking for the limit as t goes to infinity of this function right here. And you say, well, I mean, our property said, well, the limit as t goes into infinity of t over the limit as t goes to infinity of et. Well, that's infinity, and this is infinity. But you can't really factor this. There's nothing really you can do about that. So what are you to do? Well, once you learn how to like derive things, there's this cool rule called L'Hopital's rule. Oops. His name is stop that. L'Hopital. And it basically says, okay, well, if you ever have a case where you're computing a limit as, say, x goes to some a of some, I don't know, h of x, or h of x equals f of x over g of x, and both in the limit as x goes to a of f of x equals infinity. Oops, that's not infinity, and the limit as x goes to a of g of x equals infinity, or 0. I think it's or 0. Then what you can do is, if you want to compute this, is you take the limit as x goes to a of h of x is just the limit as x goes to a of the derivative of both the top and the bottom. The derivative of f of x and the derivative of g of x. That's basically what it is. If these both go to infinity or 0. I don't know if that made sense, but I hope it did. But you'll learn it later in the year anyway. But so, if we wanted to do that, sneak preview, well, the derivative of this is just the limit as t goes into the infinity of dt of t over dt of et, which is just the limit as t goes into infinity of this derivative is just 1, and this derivative is e to the t. So, and as t goes to infinity of e to the t is 1 over infinity. And that is always approaching 0. So the limit of this is 0. Anyway, you don't need to know that now. Don't worry about it. It's just cool. I thought you should know. Alright. That's all I have. And see you next time.